All right, I got a request to work exam 2, spring 2019. So I'm going to go ahead and work this as best I can. Hopefully I don't make any errors, and we'll see what happens. Okay, let's zoom in. Is that carrying everything? Yes, it is. Okay, good. So we're going to call this the key, although, I guess we'll see if it ends up being a key, but this is the video key. So let's see here. Steady flow through an expanding pipe is considered uniform. Okay, uniform means d by dx, so just some kind of direction, is a constant. So basically things are not changing in the x direction. So steady flow means it's not changing in time. And an expanding pipe means the pipe is kind of going like this. So imagine the flow going like this, and then it's going to slow down because the pipe is getting bigger. So that means that the flow is changing in the x direction. So this is not considered uniform. It's almost the definition of non-uniform. Okay, in a horizontal pipe expansion leads to an increase in pressure. So I guess I just drew a horizontal pipe, and it's expanding. And so let's see here. So the velocity here is high. So the pressure here we might consider to be low. And then over here, the velocity is low. So the pressure has to be high. Right, so pipe expansion leads to an increase in pressure. This is true. And this is just based on Bernoulli. Okay, because z is not changing. So if the velocity decreases, the pressure has to increase. Okay, in a flow field defined as, if a flow field were defined in 2D as u equals 5 times time and v equals negative 3x, the local acceleration would be negative 3. So local acceleration is defined as du dt plus dv dt plus dz dt. Okay, and let's see here. Well, this is not a function of time, so it doesn't matter. This is a function of time. So it looks like the local acceleration here, if I take du dt, I'm going to get 5. So it's not negative 3. So this is going to be false. Okay, a streamline is a line generated by a tracer fluid, such as dye, continuously injected into a flow field at a starting point. And that is no. That would be a path line. No, that wouldn't be a path line. This would be a streak line. Okay, that's the definition of a streak line. A streamline is at any one moment in time, you take a picture of the whole system. So you've got the whole system. So we've got pipes and a reservoir and whatever it's doing, and you've got this is kind of the whole system at one moment in time. Okay, I mean I don't know. I'm just making up some lines, but so this is false. Laminar flow appears quote unquote smooth relative to turbulent flow. That's true. That's kind of the definition of laminar flow. One use of the Reynolds number is to determine if the flow is laminar or turbulent. That is a yes. So usually we say, like in a pipe, we say that if Reynolds number is greater than, 2,000 to 4,000, we say it's turbulent. Okay, so that's true. The Bernoulli equation assumes that 2 points are on the same streamline. This is one of the fundamental, assumptions of the Bernoulli equation. So the Lagrangian point of view refers to a moving reference frame. That is the definition of a Lagrangian point of view. An Eulerian point of view is a fixed reference frame. For fluids, volume is conserved, no mass is conserved. But we often will write Q in equals Q out, but really we're not thinking that. Really what's happening is we've got that rho out in front, which is telling us that the mass in equals the mass out, plus accumulation, of course. But usually because the rho is constant and there's a rho here, it just ends up going away. Okay, the Archimedes Principle states that the buoyant force is equal to the weight of the fluid displaced. So the buoyant force is usually equal to the gamma of the fluid times the volume displaced. Okay, and this is the definition of the weight of the fluid displaced. So it's true. Okay, so that's that. Okay, so, hold on. Okay, so a large iceberg floating in seawater. Here's an iceberg. Here's some seawater. The iceberg has a specific gravity of S ice equals 0.9, and the seawater is 1.03. What percent of the iceberg is above the seawater? All right, so we're going to do a free body diagram here. We're going to keep this simple. There's one force coming down, there's one force coming up. The force down is the weight, and the force coming up is the force of buoyancy. All right, so if we sum forces in the vertical, sum of the forces in the vertical, we call that the z direction, equals 0. Let's see what we've got. FB minus W equals 0. Okay, the force of buoyancy, that's gamma of the fluid times the volume displaced minus the weight, which is gamma of the object. Okay, in that case, I guess in this case that's ice, right? So maybe we should just put gamma of the ice times the volume of the ice equals 0. All right, so now we're kind of getting somewhere, but here we go. What percent of the iceberg is above the seawater? So I want to know this right here, okay, as a function, as a percent, so divided by the total volume. So what I want, ultimately, is what I'm looking for here, is I'm looking for V above divided by the total volume of the ice, right? And so that really means that what I want is V ice, the total ice, minus the V below, okay? Because if I take the total ice and I remove that which is below, okay, which really we actually call that the volume displaced. Come on now. Displaced, okay, divided by the volume of the ice. Okay, so that's what I'm looking for right here. Okay, and that's kind of hard. So a simpler way to do that is to make it 1 minus volume displaced over the volume of the ice. Okay, so I'm looking for the volume displaced over the volume of the ice. If I got that, then I'm good to go. Okay, I've got an equation here where I've got the volume displaced and the volume of ice. Okay, so I just need to rearrange it to get that. There's a few other ways that we could solve this. I'll kind of do it a second way in a second. And so I'm just going to copy this equation right here, and I'll do this the other way in a second. Gamma ice V ice equals 0. So in a second I'll solve it again right here. But right now I'm going to solve this one, and I'm looking for this ratio right here, volume displaced over volume ice. So I'm going to do is gamma F volume disp minus equals gamma ice volume ice. Okay, and so then we're going to put volume ice over here. And it looks like I want to bring gamma F over here, gamma F. So I've got volume displaced over the volume of ice equals, let's see, gamma ice. What is gamma ice? Let's see, gamma ice is S ice times 0.9. So it's 0.9 times the gamma of water. And the gamma of the fluid is 1.9 times the gamma of water. So those cancel, and I'm left with like probably in the 80s somewhere, 0.8, hold on. Okay, some number like that. And then if I go over here and plug it in here, I'll say that the percent, or the, I guess the V above versus V ice, V above divided by V ice equals 1 minus 0.87379 equals 12 point, well, okay, 0.10, right? 0.12621, or the percent above equals 12.6%. Okay, so we're just going to multiply by 100. Okay, that's how you do it. Okay, the other way that we could do this is I could define the volume displaced, right? I could say, okay, well, the volume displaced is the volume displaced plus the volume above equals the volume of the ice, right? So that's the total. And somewhere in here, I want to get at the percent, or either the fraction above. So I can say, well, the V disp equals the total volume of ice minus the volume above. Okay. And then I could say, okay, well, V disp, let me zoom in over here. Okay, the volume displaced equals the volume of ice minus some number, which I'm just going to call F. So that'll be the fraction that is above, fraction above, times the total volume of ice. Okay, and this then is what I'm going to be looking for. That's what I'm going to solve for, that fraction. And they'll have to multiply by 100%. But so what we'll do is we'll say volume displaced equals 1 minus F above times the volume of ice. Okay, so I can take this quantity, I can plug it right there. Okay, I'm going to solve straight out for F above, right? So now I got gamma F times 1 minus F above times V ice minus gamma ice, V ice equals 0. And what you'll see that's nice about this is this V ice goes away. Okay, and then there's going to be a gamma of water that's going to go away, because this gamma of the fluid, well, that's S of the seawater. Sorry, I didn't want red there. S of the seawater times gamma of water, and the gamma of the ice is going to become the S of ice times the gamma of water. Okay, so, the gamma of water is going to go away. Okay, so I'm left with a nice equation, SSW, 1 minus F above, minus S ice equals 0. Sice. All right, so then we can solve this equation by plugging in 1.03 times 1 minus F above minus S ice, which is 0.9. Come on, you can do it. There you go. 0. Come on. 0.9 equals 0. So if you solve this mathematically, it comes out exactly like this. So F above equals, so 0.12621. So the percent above equals 12.6%. Okay. So that's just an alternate way to do it. Neither better nor worse. I typically solve it this way. It's just, I don't know. It's more steps, but I don't know. I just like it. Okay, so let's go over here. The level of the tank below is increasing at 0.05 meters per second. So this thing is going up at 0.005 meters per second. If D is 4 meters, so this is a 4 meter, and Q1 is 0.04 CMS, that's cubic meters per second. What is Q2? Oh, well, this is an easy question. Perhaps the easiest question I could have ever asked. Okay, so we're going to go in equals out plus accumulation. Okay, so let's define our control volume. Here it is. Okay, so I'm going to go above the water surface. There are, of course, other ways to define your control volume. So the N is Q1. Well, it's going to be rho Q1, rho 1 Q1 in equals the out, which is rho 2 Q2 out. And then the accumulation is the cross-sectional area of the tank. Well, let's let's not get ahead of ourselves here. Okay, is the change in the volume, or the change in the mass of the tank. So rho times the volume. Okay, and that's in the tank. Okay, so let's see here. So rho 1, rho 2, and rho in the tank are all the same. Sound effects are key. Make sure you're making your sound effects. Q1 equals Q2. Oh, wait. Divided by the change in time. Okay, sorry. So plus the change in volume over time. Okay, so the d by dt, we're going to make it an integral of volume. Okay, and the volume in this case is the area times the height. Okay, so the area is this area, and the height is this height. Okay, we're going to take this area out of here because it's constant. So I'm saying Q1 equals Q2 plus area times dH dt. Okay, Let's see, we know, so now we know everything we need to know. Okay, so Q1 is 0.04 cubic meters per second equals Q2, which is what we're looking for. I assumed, by the way, that it was going out. We don't know. It could be going in. And then the area is pi times the diameter, which is 4 meters squared divided by 4. Okay, so that's 4 pi meters squared. And then dH dt, well, how fast is that height changing? 0.005 meters per second. Okay, so we plug all this into the calculator. Okay, and I get negative, 0.0, whatever this number is. And so that negative sign means I assumed the wrong direction. So it's going to be 2.28 times 10 to the negative 2 cubic meters per second, and that's going to be in. Okay, so I assumed it was out. Turns out it's in. Okay, so this would have been worth some points on this, however I graded it. Okay, I still remember this problem, and I'm still upset that you asked me this one because this was a problem that was too long for this test. To do the X and the Y direction. But we'll go ahead and do it. Water pipe throws through the 30 centimeter long. So 30 centimeters is going from, give me a pen please, from here to here. 90-degree bend in a 2-inch diameter pipe. Okay, so it's 2 inches this way. Okay, and it is 30 inches long this way. The flow rate through the pipe is a constant. So we do know Q. It's always nice to have Q. Q equals 0.6 cubic feet per second. The pressure at the top and left side of the bend. So right here we've got a pressure of, what is it, 19.4 psia, 19.4. I don't want to use that, and I don't want to use that because they're in psi. So that's totally annoying. Respectively, calculate the reaction force required to hold the pipe bend in place. Okay, but I don't like those pressures. This 19.4, I don't like it. The reason I don't like it is because it's absolute, and I want to work in terms of gauge. So what we're going to do is we're going to convert this to gauge. We're going to convert both of these to gauge, and the way you do that is you subtract off the atmospheric pressure, which in PSI is 14.7, and then you're going to multiply by 144 to go from PSI to PSF. Okay, so ultimately that's going to give me 676.8 PSF gauge, and this one's going to be 1324.8 PSF. Okay, and that's pretty key. Okay, so we're going to go over here, and I'm going to say this is 676.8 PSF, and then right here I'm going to have to do 1324. Oh no, don't do that. Let's undo that. Okay, that was a weird thing. Okay, 1324.88 PSF. Okay, what else? What other forces do we have on this thing? Well, in blue we have this, this momentum flux here and this momentum flux here. And we've got a weight, right? We've got a weight. Well, I don't want to do that in blue because that's a force and not a momentum flux. We've got a weight right here. It's the weight of the water, and we're only concerned about the weight of the water because it says you may assume the mass of the bend is negligible. Okay, this problem would have been totally fine difficulty level for a test. Unfortunately, I should have asked for either the X direction or the Y direction and not both because this thing just kind of got time consuming. So they already gave us an R, so we're going to go ahead and use that. I'm just going to assume that we've got an RY and we've got an RX, okay, because anyway. So here's the X direction. Okay, at this point you should know this formula, the sum of the forces in the X direction plus rho VQ. Okay, that V is in the X direction. This is in equals rho VXQ out. Okay, so the forces in the X, we've got P1A1, or Pn, I guess. Let's call this 1. Let's call this 2. So let's zoom in a little bit. Okay, so I've got P1A1 plus, I've got an N, so that's going to be rho at 1, whatever that V at 1 is. And I've got the Q. Do I have any other x forces? Oh yeah, I've got minus Rx. And here it looks like we just assumed it's going to the negative. We're not sure if that's true or not. Oh, well, okay. I forgot that it's one of my sum of forces, right? So, yeah, so when you screw up like that, you got to step back and make sure you get it right, okay? And there's no out in the x direction, so this term goes away. Okay, so here we go. So we got negative Rx plus P1, which is 1324.8 PSF, times A1, which is pi times 2 inches, 2 over 12 feet squared, over 4, plus rho. Did they say this was water? Water. Okay, so the rho of water. Okay, be careful here. 1.94 slugs per cubic foot. Okay, what's the velocity of one? Well, the velocity of one and the velocity of two are the same thing. We didn't figure them out, so let's go here. V1 equals Q over A, and that's also V2. Okay, so the Q is 0.6 CFS. Okay, and the area is pi times 2 over 12 squared over 4. So V1 equals V2 equals whatever that comes to. 27.502 feet per second. Okay, so we'll go down here, and here's our V1, 27.502 feet per second. And then we need a Q, which is 0.6 cubic feet per second equals 0. Okay, so let's see here. Cubic feet here is going to cancel with cubic feet here. So we get slugs feet second squared. So this is all pounds. PSF times square feet. So this square feet is going to cancel with these feet squared. So I'm going to have pounds there. Okay, so Rx equals 60.915 pounds. Okay, so that's, and I got a positive, so it's actually, so Rx equals 60.915. I assumed the correct direction, which means it's going this way. Okay, now let's do the y direction. Okay, sum of the forces into y plus rho Vy Q in equals rho Vy Q out. Okay, what are the forces into y? Let's see. Let's go back to our picture here. We've got that weight we're going to have to deal with, right? So first, let's not forget this ry, which I drew in as positive. Ry minus the weight of the water minus P2A2. Okay, what else might we have here? I think those are all the forces. All right, let's see, here, here, here. I think that's it. Yeah. Okay, and then we've got a, we don't have any fluxes in, equals rho times V2 times Q, because that's leaving, right? Now V2, it turns out, is positive. So both of my velocities in this problem were positive. So that kind of made them easy-ish to deal with. So that's the unusual thing about this. On a test, I almost always make sure that there's a sign that you have to deal with, because I want to make sure that you know how to do that. So the weight of the water in this case is the gamma of water, 62.4 pounds per cubic feet, times the volume of water, which in this case is pi times 2 over 12 feet over 4, that's the area of the opening, times the length of the pipe, which I think is 30 inches. So 30 over 12 feet. All right, minus, here we go, P2A2, 676.8. 676.8 PSF. Okay, times the area, which is pi times 2 over 12 feet squared over 4. If we'd been smart, we would calculate that area at the beginning of this problem, because it's come up constantly, equals the density of water, which is 1.94 slugs per cubic feet. Okay, times the velocity, which we calculate up here, 27.502 feet per second. and then Q, which is 0.6 cubic feet per second. Okay, so that's a lot of stuff. Let's see. Yeah, so if we do all of this right, we're going to get Ry equals let's see here, 50.179 pounds. Okay, and we assumed upwards, so it's going to be Ry equals 50.179 pounds upwards. Okay, so now we need to get R, and R then equals, let's see, the square root of 60.915 pounds squared plus 50.179 pounds squared. So R equals 78.921 pounds. And I need the angle, so theta equals inverse tangent of, let's see here, 50.179 pounds divided by 60.915 pounds. Okay, so theta equals 39.5 degrees. Hold on. Let's call that a 480. Okay. So then your final answer here is R equals 78.9 pounds at, so this angle right here, well, let's see here, that's 50 up and 60 to the left. So we're going to measure this from the left. It's going to be like that. Okay, 39.5 degrees. Okay, and there's your answer. Okay, and then let's see. All right. So boom, moving right along. This is always the doozy. I always like to have a nice, complicated doozy. And at this point, hopefully you guys have seen enough of these. I love this problem. I've done this one a million times now. Anyway, so estimate the flow rate through the Venturi meter shown below. Okay, so we're going to pick our control volume, and we want to pick it in places where we know stuff. Okay, so I'm going to do it from here to here. Okay, this is my control volume, or whatever. My streamline that I'm working on is going to be from this point right here to this point right here, which for some reason are coming out as, okay, so this will be point 1, and this will be point 2. Okay, 1 and 2. Okay, so I'm going to start with, looks like I got a lot of space over here, so we're going to use it. Okay, I'm going to start with T1 over gamma plus Z1 plus P1 squared on 2G equals P2 on gamma plus Z2 plus V2 squared on 2G. Here's my streamline connecting those two. Okay. Now I already know, so I'm going to go ahead and start arranging things. I already know that I'm going to do this, right? I'm going to bring P1 over gamma over there. Z1 minus Z2, go ahead and put that over here too, Z2 minus Z1, because I'm going to make that like some kind of imaginary letter, like a lowercase h or something. And then, let's see here, V2 is going to be faster than V1, so let's go ahead and, you know what, let's bring it all over to one side. Let's have fun with this, okay? V2 squared minus V1 squared on 2G. All right. Okay, so here we're going to have a datum right here. Hello, my datum friend. Here's another, and this is going to be another point, right? And I'm going to go ahead and call this lowercase h. I'm going to go up to here. Okay, there was a problem somewhere in the text, in an old textbook or something that used these letters, and so I just keep using them, and it doesn't really matter. So Z1 minus Z2, that's the easiest one of these to get, so I'm going to go ahead and do it right now, because Z2 minus Z1 is h, or we can say that Z1 is 0 and Z2 is h. Now I need P2 minus P1, so I got to do a manometer. So I'm going to start at P1, and I'm going to go up, minus the gamma. Is this water? Oh boy, it didn't even say, did it? Well, that's problematic. We're just going to call it water. I think it won't matter, actually. as long as, because this is the fluid. So we'll make all of these waters. Anyway, I think the gammas are just going to straight up cancel out, so it's going to be okay either way. Anyway, yeah, so, all right, so anyway, we're going to go up in the water. H, lowercase little h, plus big H, plus 48 inches, plus 4 feet. Okay, that gets me here. Now I'm going to add, so now we're going to go over here, and I'm going to go down gamma air times 4 feet. Okay, and now I'm going to go down from here to 2. So I'm going to add gamma water times capital H equals 0. Okay, so that's a little bit crammed, but it's not equals 0, equals P2. P2. Okay, so I'm going to rearrange this. So we're going to end up with P2 minus P1 on the on the right, and then I'm going to divide by gamma water. Okay, when I divide by gamma water, that means I'm going to end up with negative H minus 4 feet plus gamma air over the gamma water times 4 feet plus capital H. And that is an ugly looking equation if ever I've seen one. That's okay. This is going to go away with that. All right, so now I get P2 minus P1 over the gamma of water equals, let's see here, gamma air over gamma water times 4 feet minus H minus 4 feet. Okay, we'll note that gamma air over gamma water is really, really small. It's like 0.001 or something. So this is basically we're just going to ignore because it's small. If you wanted to, actually, you know what? Let's include it here. Let's just include it and see what happens. See how much it affects the answer here. So we'll go here and we'll say P2 minus P1 over the gamma of water. See, did I include it in my key? No, I did not. So I have a key online, and we could just see how much not including it affects the answer, or including it or whatever. So anyway, gamma water, which is given in this air, is given as 0.20. 0.20 pounds per cubic foot divided by the gamma of water, which is 62.4 pounds per cubic foot, okay, times 4 feet, minus H minus 4 feet. Okay, so P2 minus P1 over gamma water equals, okay, something minus 4. And we get negative 3.9872 feet. Okay, whereas obviously if we had ignored that, we would have just gotten negative 4. Instead, we got 3.9872. Okay, so you can see, certainly for this problem, it's probably not going to make much of a difference. But we'll run with it. Okay, so we're going to take this number, and we're going to plug it in up there, right? So now I'm left with, so I'm just going to put like a line through it to say we've accounted for that. Now we need to do V2 and V1. Okay, and the quickest way to do that is to note that this is 3 times the diameter of this one. Okay, note that V1 is 3 times the diameter of V2, which means that, so I can tell you right now that V2 is going to be 9 times as big as V1 because we just square that difference, but we can go ahead and solve for it. Say V1A1 equals V2A2. Okay, so V1, here's the area, pi times 12 inches, which is 1 foot, squared, over 4, equals V2 times pi times 4 inches is 1/3 of a foot, squared, over 4. Okay, and I can say these pi's over 4's go away. So now I've got 1 foot squared on this side times V1 equals V2 times 1/9 of a foot. 1/9 of a foot. Foot squared, I guess. Foot squared. Okay, so we rearrange this, and I can say 9V1 equals V2. Okay, which is exactly what I knew right off the bat. Okay, so now we can go over here, and I'm ready to go with this one as well. Okay, so I'm going to go ahead and mark a line through that one. All right, so let's solve this sucker. 0 equals, yep, come on. Negative 3.9872 feet minus h plus h. Okay, so we're just kind of tracking down. Plus v2 squared, so that's 9v1 squared minus v1 squared all over 2 times 32.2 feet per second squared. Okay, so these h's are going to cancel. Okay, this becomes 3.9872 feet equals, this becomes 81 minus v1 squared, so it's going to be 80 v1 squared. And I suppose I need to create put an equal sign here because I've actually got a 2g that need to squeeze in there, right? So we're going to have 3.9872 feet times 2 times g, 32.2 feet per second squared. Okay, so v1 then equals 1.7916 feet per second. And if we're going to go ahead and get q out of that, we need to say q equals v1a1. I know we're like making a mockery of this grid at this point, but q equals 1.7916 feet per second times the area, which is pi times, what was the diameter here? At 1, oh, it's 1 foot. 1 foot squared over 4. So q equals 1.4071. That's cubic feet per second. So q equals 1.41 cubic feet per second. Okay. And if we look at the answer from the key, online, I got q, I used more significant figures, but I got q equals 1.4 if I round CFS. So it ended up being identical. Okay, so so this is from the key. So the only difference between these two is this one said the density of air does not equal 0. Okay, so it doesn't matter. Just ignore the density of air. Okay, so that's it. 37 minutes to solve this one. This was a totally reasonable test. The only problem was this problem here ended up being a little long, but the difficulty level was not too bad there. This one was very easy. This one was a little tricky, I guess. This one's a little tricky, depending, to deal with getting that percent. This is like one of my favorite types. This is a fave. Okay, so these show up all the time. I like this one because it uses everything. If you notice, we have to use manometers. We have to use Bernoulli. We have to use some geometry. So I love that question. So that's all I got for you. Hopefully this is helpful. And, all right. Thanks, guys. Bye.